Good evening. Today I will be taking you through my implementation of an emulated distributed file system. I will be taking inspiration from some of the more traditional distributed file systems available in the market today. To name one particular file system which I will be citing often is Adobe. To give you some context, Hadoop is broadly divided into two components. The first one is the storage component of Hadoop, known as the HDFS. And the second is the MapReduce framework, which is responsible for the computation side of things. For my file system, which I will be referring to as JSON DFS, I will be implementing these two major components. For the storage side of JSON DFS, I will be making use of MongoDB, which is a NoSQL document-oriented database to store all the metadata and actual data in the files and directories. Let me take you to the Mongo Atlas cluster console. So as you can see, I have already spun up the Mongo instance, and I have created the three collections that are required for my implementation. So for the HDFS component of Hadoop, it consists of mainly two things. The first one is the name node, which contains the metadata of the files and directories. And the second one is the data node, which stores the actual data associated with these. All right. For the name node, I have named my name node as inode list. And as you can see, it contains directories and data files. So this one, movies.csv, is a file that I've already uploaded, and it contains file path, file type, name, number of partitions, the parent, and the partition location for every partition. And for folders, obviously, we don't have the partition. Instead, we just have the folder path, the type, and the name associated with them. In addition to this, I've incorporated the parent element, which makes it easier for me to implement the ls command. And I have created a separate collection for the parent-child relationship too. So for example, if my parent is AD, my child will be P1 and directory 1. Moving on to the data node, which is the actual hub for all the data that is stored in my DFS. I have already preloaded a dataset called movies.dataset, which is nothing but the IMDb related information for several movies. And I have partitioned that into three partitions: movie 1, movie 2, and movie 3. So movie 1 contains an array of the data objects, which is like every particular movie. And then movie 2 contains a subdivision of these data objects. Similarly, movie 3 also contains a subdivision of the remaining objects. Now I will take you through my implementation of JSON DFS, and I will list you all the search commands and also the analytics part of things that I have implemented. I have implemented run.sh file so that when I click on it, it automatically takes me to the JSON DFS shell. I have also helped the user to understand the JSON DFS command by listing several search options. The first one is the KLinex, which is responsible for the storage and computing related information. I can see all my commands here along with their syntax and example. To take you through a few of these, I will be implementing and demonstrating a few. First, I will start off by making use of the ls command. ls/ refers to the home directory, and this will list all the items available under the home directory. Moving on, if I want to view the files under AD directory, I can just directly give it like this. And this also contains subdirectories P1 and dir1. Similarly, AK directory contains another directory called A. And the last directory contains my movies dataset 5, and also another CSV that I've uploaded. And for this purpose, I will be limiting my uploading capabilities to only CSV files because it's easier for the user to correlate and understand with my DFS. In the future, I might implement it to be extendable to other data types as well. And the second command I want to go through is probably mkdir, which helps you to create a directory in my DFS. And let's say mkdir sample. Subsequently, the sample directory is created, and we can do ls to view the sample directory, which is right here. I can also do other things like remove files, display the content of files, upload files onto JSON DFS. And for that, I will be first removing p.csv and re-uploading this file. So let me demonstrate that to you. So the syntax for that is rm, the file path. In this case, it would be .csv. Subsequently, the file would get deleted and I would not have that file in that particular directory anymore. Now, on the other hand, I can even re-upload the file to another directory, let's say sample that we just created. So I'm going to put my p.csv into the sample directory, let's say 4 partitions. Now the p.csv has been uploaded to sample. Yeah, see, so there is the p.csv with number of partitions as 4. The next thing I want to do is to display the contents of p.csv. For that, we will be using the cat command. The syntax for that is cat followed by the file path. p.csv. That displays all the content of the p.csv file. I can even get the individual partition data by doing the read partition function .csv, and I want to subsequently read, let's say, the third partition from b.csv. That gives me Aditya, which is what is present in the third partition file. Finally, I would also read, get the partition locations for all these partition files. This gives me the list of the 4 partitions in my local system. Apart from creating the data node online, which I will be using for search-related queries, I have also created a data node in my local system to store these files. So I put up 3 data nodes, and it randomly chooses a location to upload the particular partition node. So p3.csv, which we saw earlier, should ideally contain only Aditya field or the record known as Aditya. It's loading. Yeah, as you can see, it contains just the record Aditya. Now that we have seen all, or just to make sure, there's also the data node, which is updated parallelly. So there's a p1, a b.csv with the first partition. It contains the object Akash. Second partition contains the second record. In this case, would be Aditya. And it goes on and on. So I have made a local data node as well as the online database data node. This is all there is to my storage server related K-Linux services. And next, moving on to the search commands. Moving on to the search related queries. First, I would like to tell you the command to look up the search queries, which is ksearch in this particular case. And I have implemented 2 major types of search queries in my engine. The first one being the built-in queries and the user-defined queries. The built-in queries is primarily a wizard which enables the user to understand how KSON DFX works, and it's implemented currently only to the movies dataset. And if we try to enter some other dataset, let's say the b.csv that we uploaded earlier, it gives you a message displaying that it's currently only available for the movies dataset. So let's demonstrate for the movies dataset. The built-in functions are three functions in this scenario: OP1, OP2, and OP3. And OP1 gives you the top X movies which are family friendly to watch. OP2 gives you the top X rated movies in ascending order. And OP3 displays the top X movies with the least runtime. Let's say I want to implement the OP3 operation with a X value of, let's say, 7. So this automatically displays you the partition and the combined results. The partition results are the results coming out of each of the 4 partitions of the movies.csv file, which is individual map phases. And after map phase, we send everything to the reduce phase, and we group by and combine all the results by displaying only the top 7 elements with the least runtime. And this gives the user a rough idea of the MapReduce framework as well. Moving on from the built-in queries, we have the user-defined queries, which requires a user to understand a little bit of syntax and a basic understanding of the way KSON DFS works. So the first is a default KSON DFS function, followed by the name of the dataset that we want to query in. This is immediately followed by the attribute or the column that we want to do the search query for. And that is followed by the 3 major operations: EQ, in, and range. EQ checks for equality between the column and the value we enter subsequently. In is majorly used for array-based elements. Let's say, for example, in the movies.csv dataset, we have a column called stars, which refers to the movie stars. So you can check if the Johnny Depp is part of the stars array and display those records in which he acts for. The last one is the range query, which gives you a rough estimate of a range between A and B for numerical based columns. And I will also like to give you a rough understanding of columns available in the movies.csv file. I've created a separate search/help command for that, kdatasets description. And it has a title attribute, it has the genre array or the stars array, which I mentioned earlier, along with the rating information, which is an integer. So let me implement a few of these commands. So based on DFS, let's say movies.csv. I want to query, okay, maybe not movies.csv. b.csv that we created earlier, I want to query for the name and equal to. I want to search for Akash and only maybe the name and the age columns. And I have implemented an explanation facility, which gives the user the flexibility to display the result in either partition and a combined view, as we saw earlier, but the explanation is much more detailed in order for the user to understand the MapReduce framework or just the combined overall result. In this scenario, I would give you a demo of the explanation facility. So the explanation facility is like divided roughly into 2 phases: the map phase description and the reduce phase description. The map phase description gives you an idea of a map function being applied to every partition of the file and querying for the name Akash. In this case, the partition 1 did return a result, but partition 2, 3, 4 did not. For the reduce phase, so this just directly grouped by and combines all the partitioned results. Since this is a basic search command, we don't need to apply any aggregation. Otherwise, the reduce phase would normally include an aggregation operation. There is something also I wanted to allude to, which is the combiner. So for analytical based queries, which I have not implemented because I am doing the project individually, there is also something called the combiner, which you can implement before the reduce phase and as a part of the map process or after the map phase. So combiner is a mini reducer which applies the same aggregation that is applied to the reducer, but in the map phase. The second demonstration command I wanted to give you an idea was the range operator. So KSON DFS, movies, or CSV. Let's say I want the rating range. I can give you the value lower bound A and the upper bound B. Let's say 8.2 and the upper bound is 8.8. And I wanna display the title and stars of the movie. In this case, I would say no, as I've demonstrated the explanation facility earlier. And this is the combined resource. So it gives me the entire partition combined resource. And all these movies have a rating between 8.2 and 8.8. And finally, the last thing I would like to allude to is the error handling that's in place on my system. So if I, instead of case search, if I miss a character, it automatically displays error incorrect command. Or for example, if I do an incorrect ls, it would be something which does not exist, it does not return any path because this particular directory is not there in the DFS. To exit my DFS, I just need to type the command exit. It automatically takes me out of the shell. As a part of my project, I have also made an extensive report. The last thing I would like to probably show you is the report that I created, the extensive report as a part of my project. It contains the aim of the project along with the project design. And there are three major components. First, the search or the storage related component. Second, the MapReduce framework, which implements the search component. And third is the command line interface. And the command line interface, to tell you more about it, was implemented as a part of the terminal, and it gives the user extensive capabilities. Like, for example, let's say the explanation facility as a part of the search capabilities. Also, the basic error handling in my project, which was extensively worked on and checked for each and every particular command. And the last one being the help or the guide related commands like ksearch, which lists you the various search commands, or klinux, which lists you the various Linux-based commands. I have also given a rough idea of my learning experience from developing the system. And as a beginner to distributed systems, I did not have a lot of extensive knowledge on this. But this project gave me an understanding of SDFS, MapReduce, and the different components of Hadoop, and also the several distributed system environments that are available in today's market. Through the use of MongoDB, I also gained an understanding on the use of NoSQL and the advantages and disadvantages with respect to SQL versus NoSQL. I have also given a link to the folder containing my code to just show you a rough overview. My implementation is divided into two files. The first one is where I implement all the storage related commands, and the second is primarily for search related commands. And I just combined both the files, and I'm just importing the search functions that I created from the second file and using it in my main KSON DFS file. And that's it about my project. Hope you guys had a good understanding from my demonstration, and thank you so much.